Hey everyone, my name is Charlie Como and this is my video lab report for our fourth lab. Our goal here is to explore time and non-time dependent voltage and current in a DC and an RC circuit. The fundamental physics principles used are charge and energy conservation via the loop and node rules respectively, and we will use an online simulator to model a perfect real-life experiment for data collection. Our first circuit looks like this as shown. Using the loop and node rules, we can predict the values for the current in resistors 1 and 2, which come out to be equivalent because the circuit is in series and is about 0.02 amps. After recreating the circuit in the simulator and measuring for current, we find that our prediction was indeed correct. Note that reversing the direction of the ammeter does not change the value of the measured current itself. Now let's replace one ammeter with a voltmeter as shown. Our simulator measurements show that while there is no current present in this open circuit, there is still a potential difference between the two hanging ends. I would like to note that we can prove this mathematically by modeling the open section as a resistor of infinite resistance, which using Ohm's law shows a resulting current of 0 amps and a potential difference of just the total potential difference, which is 3 volts via the two 1.5 volt batteries. After closing the circuit, we can use our voltmeter to experimentally measure and confirm the node rule, where the sum of the potential difference of all non-wire components is 0. Additionally, we can use our new volt values to recalculate our resistors and find that our new values do confirm Ohm's law. Now we can make a potential versus position graph of all our circuit components, which visually helps to see that the voltage from the batteries equal the total voltage due to the resistors. If we put our ammeter in parallel with the 100 ohm resistor, we will redirect all the current from that resistor into the ammeter with no resistance, because the ammeter will become the path of least resistance, which will decrease our total resistance and increase our current to 0.064 amps. Now we will look at RC circuits in series. After first closing the current with the battery, the brightness of the light starts bright but becomes dimmer over time until it stops shining. This is indicative of a buildup of charges at the capacitor that is slowing down the current. After removing the battery, the capacitor begins to discharge, with the light again starting bright but becoming only more dim over time, indicating that the capacitor is running out of charge to make the current flow. Note that the measured charge and discharge times are essentially equivalent for circuits with the same resistors. In order to better analyze this time dependency, we can use the node rule to help derive an equation for the potential difference over time, which after taking advantage of log properties, we can plot a linear line using initial and current potential difference, time, resistance, and capacitance, with the slope being the time constant. This was how I pulled my data, and after logging it into Excel, I produced a fantastic line of best fit with a perfect r-squared value and a slope of negative 0.167. Using our mathematical models, we find that our time constant is also negative 0.167. Lastly, if I were to do this lab in real life with an actual ammeter, some result differences would be that a real ammeter would have a resistance of its own instead of having none, which would increase the equivalent resistance and create a lower current for our circuit. And if I used a real battery to charge the real capacitor with no resistors, the capacitor would not be fully charged instantaneously because the batteries would have internal resistance, which would make sure the capacitors are not instantaneously fully charged as predicted by the simulation. Additionally, my measurements will be further influenced by the fact that battery strain and equipment's wear and tear. Thus, it is highly likely that my measured values will have a larger error compared to the predicted model. And that is my presentation, and thank you for watching.